We're rolling already?
Yeah, we've been rolling.
Nice. So who we get the review the tape because we just said some spicy things.
That's fine. If you're interested in some good merch, then head to merch.techtechpotato.com. The move from CTO to CEO, briefly touch on how's that been for you? Officially it's been a couple of weeks.
Yeah, it's probably really been a couple of months. It's fine. So, I came to Tenstorrent to support Tenstorrent and Rubici any way I could. We're starting to expand our business. We're talking to way more customers. We're in the process of raising some money. We're talking to investors. Like the next year is going to be massive distractions. And then I've hired some additional staff. You've met David, we met Bob, we hired Keith Wittick. We're bringing a few other people on board to expand our ability to do stuff. Labicia's basically been on fire working on software stuff. I think, for both of us, it's been good. We need to go make some money. We need to execute on a bunch of things, but the fundamental challenge of the company is technology development. And the software problem is mysteriously hard, as everybody knows. And we think we're making real progress. So, I'd say on the whole, that's been pretty good.
Speak to a lot of machine learning companies, and obviously they have the hardware strategy, and whether that's just SIMD engines in parallel or something a bit more esoteric, they all say the software problem's hard. Mm-hmm. So what are you guys doing differently?
Yeah, well, so I was explaining this to somebody. It's like the software is almost too easy and it sucks you into it. So if you just look across the spectrum, so modern CPUs are really hard. Mm-hmm. Out of order execution, it takes pretty experienced people a lot. But we run, C programs essentially at the bottom. No matter what you do, the hardware-software contract is really clear and actually really old. And that definition is pretty good. And then you go to GPUs where the thread engines are pretty simple, but you have 1,000 of them or a lot. And then the genius of CUDA was you write what looks like a single-threaded program per thread. And then there's a coordination layer to do that, and sometimes it works great, and sometimes it doesn't work so great. So the hardware is much simpler than the CPU at some level, but the software contract is more difficult. And then you go to AI and you say, well, we're just going to run big matrix multiply, tensor transformations, convolutions. The hardware at some level is simpler, but it's like in the inverse proportionality. Yep. Like the CPU, the software is simple, and the hardware is hard. In AI, the hardware is simple, and the hardware is simple, and the software is hard. And it's harder than it has any reason to be because the number of operators. I gave a talk and said there's only 5 main operators. Matrix multiply, convolution, tensor transformation, GLO, softmax. You could argue about some other details. How hard could that be? Well, it's running on thousands of processors. It's got local memory, global memory. It's got communications. It's got, you name it. It's got every problem in the book, and all these things turn out to be, stupidly hard to coordinate and do. So what are we doing different? We've never put hundreds of people hand coding some benchmark. That's been a fail.
Yep.
Right, and part of the reasons there's so many pivots. So there was inference and training, and there's language and vision models, and then there's sort of big and little models, and then there's generative models, and then stable diffusion and models like that have multiple features inside of them all at once. They got image and language and backpass, and it's pretty complicated. And if you start chasing one of those, long before you're done on that model, the new thing will be out, and the hand coding stuff doesn't work. So our mission is you write AI programs and it compiles performantly, and we're starting to crack that properly. And our test is we have a library of popular models, and we're running most of them, most of them performantly, and we're on our way to getting all of them, and most of those performantly. And then the other thing is, we want to scale from a single chip to many chips in software, not have many layers of software between, like how you code your AI model and how it gets deployed. And we've demonstrated some models on a large number of chips. We're working to make that, more productizable, and that's making pretty good progress too.
So spending some time with your team here, and despite there being industry layoffs, you guys are hiring.
Yes.
With that pivot to that sort of more focused software mentality, do you find that people that are coming into the company have to switch their traditional thinking a bit to what they're used to?
No, not really. So first of all, our software team is relatively small. We're hiring people who really get. So it's interesting. So there's high-level programmers who write JavaScript, all kinds of things. There's lots of people like that. Those are hard in their own domain. And then you sort of have system-level programmers, people who know operating systems, all kinds of details. And then you have we used to think of low-level programs, people who can program on the hardware. And then in the compiler stack, there's the same kind of thing. There's high-level language features, and then there's the mid part of the compiler, and then there's still low-level details. The kind of people, we need people who understand system programming and compiler from pretty much top to bottom. And when you find the right people, they like it. And then the other funny thing is, Tenstorrent started with people with FPGA backgrounds, synthesis backgrounds, and HPC backgrounds. Because AI is kind of a combination of those. And they don't grow on trees, right? So people come in with different things, and they have to sort of be into hey, I'm going to build a software tool chain that part of it looks like synthesis, and part of it looks like an HPC problem, and part of it looks like low-level driver code. And we hire what we think are good people, and then you have to find your place in the software stack. It's a little different from the standard kind of delineations in the software stack, but we've had good luck. We like the people we've hired.
So, been speaking with Weihan, your RISC-V chief architect.
Yes.
Why do you have it's a two-part question really. Why have you got cores in your AI chip at all, and why are they RISC-V cores?
Yeah, there's a couple. So why RISC-V processors at all? So first, our Tensec processor has 5 little RISC-V cores in them. We call them the baby RISC. Right, and they do stuff like fetch data, execute math operands, push data around, manage the NOC, do some other things. And they're RISC-V partly because we could write it and do what we want. We don't have to ask anybody for permission. We could change. The baby RISC actually leaves some stuff out. It's pretty simplified. And in a future generation, we enhanced the math capabilities and fixed a whole bunch of stuff so we can talk to the local hardware control pretty directly. So it's ours. We can do anything we want. We put in RISC-V in our next generation chip, which we're taping out soon, part because we went and asked the other vendors to add some floating point formats for us, AI. So we're keen on AI floating point formats, accuracy, precision stuff, and AI programs have to be, because you want to drive the small floating point data sizes, but maintain the accuracy across billions of operations. And the RISC-V guy said, sure. So we called Sci-Fi and said, can you do this? And I said, sure. So we did. So that's why RISC-V is in there now. In the future, we think AI and CPU integration is going to be interesting. And we want to be able to do what we want. And I don't want to have to ask somebody for permission to add a data type or add a port from a processor to this or change how the data movement engine works. I just want to be able to do it.
You're also moving into chiplets. And
yes.
Machine learning chiplets, CPU type chiplets. Yeah,
there's a couple of drivers. One is 3 nanometers is really expensive to tape out. So everybody knows that.
Yep.
The other is you want to drive forward on the compute in terms of density and power efficiency, but all that I/O part doesn't care that much. a big driver is the packaging technology has moved to the point where you can get fine pitch, good low power die-to-die PHYs and do what you want. Now, the dream is then you have an AI chiplet, CPU chiplet, NPU chiplet, a couple kinds of memory controllers, a couple kinds of PCI Express controllers, and then you can build a product out of an assemblage of different chips. And you could say, well, that's kind of like a board, but now it's in a package. And it's in a package where the chip's a butt with really short wires, so the power efficiency of chip to chip at high bandwidth is really good. We suspect the next couple of years is going to be growing pain problems. We've talked to quite a few people about it, and what I think is going to happen is if you have a solution you really want and you're building this chip and somebody else is building another chip and you work together and co-simulate, the odds are good that it'll work together. And then the cool thing then is you can build more products with less tape outs. And I also think it's going to lower the bar for some kinds of products, lower the cost bar. And yeah, so I think it's a really good idea. A couple of things are driving it. The need for it, the cost, the package availability, the willingness of people to cooperate across these domains. It's going to, but like anything, this is not going to be easy. This is going to be a complete bloody mess. And I predict a year from now, I'll be thinking, geez, why did we get into this? We should have waited for somebody else to take the arrows. But whatever.
So, okay, let me address that. Mm-hmm. What you're going to field next year. The way Tenstorrent currently has its roadmaps with Blackhole, Grendel, and this chiplet design, and the announcement of Ascalon, and this multiple design points for Ascalon, is Tenstorrent we think of as an AI machine learning hardware company. But if you've got chiplets and there's all different sorts of IP, are you actually selling products, or are you selling IP, or what's the business strategy here?
So I've thought about this because to me it's relatively clean, but the world's complicated. And I'll give you an example. Like if you make a C compiler, nobody asks you if you're in autonomous driving or industrial controls or data center. It's a C compiler. That's a technology. That technology can be used in anything, right? So we're a design company. Like our A game is we design AI hardware, CPUs, and AI software. Like we design, that's what we do. That's what everybody comes in and does. Now, we're going to sell products. The hardware product we're going to sell is AI computers, right? And we'll sell a chip, a board, or a system. We also have a cloud so people can come try it out and onboard. And also some people don't really want to buy computers. They want to use clouds. So that's a product to sell. But we can also sell our AI chiplet and our CPU chiplet as a product. Those are technologies we design that people can go use to do a bunch of stuff that maybe we're not going to do, right? Now, the funny thing is when we showed people our plan, here's this AI chip, and then we're going to put in RISC-V processors because we want local compute in the die. We started by licensing a processor, but then we built a team who, let's say, outperformed our targets. So we have this, really great CPU team. And then people said, hey, could I buy that CPU? Well, I didn't really want to sell CPUs as a product. That's a big, complicated market, but other people wanted to. So we're going to license the CPU and also sell that CPU on a chiplet where people can embed in their own product. And that's turned into really interesting conversations with the company because they're like, well, I'm building this thing, and the last thing they want to do is pay a license fee to license a CPU and then have to harden it, which takes a lot of expertise. Having a CPU chiplet that they can put in their package that does what they want. And if, and there's, by the way, there's other people doing it, and if they want the other people's, that's great. And if they want ours, we'll sell it to them. But we're a design company, and then we're especially with CPUs, especially when you build a complicated CPU, you want multiple targets for that. Because to get it right, you simulate it yourself, you partner with somebody, they simulate it. I promise you they'll find bugs you never thought about. So, we've been keen to find some good technical customers for that, or they're going to be partners when we're debugging it. And but Tenstorrent, we're a design company first. We have great architects, and then the thing that's growing that's really hard is AI. the thing that's, well, I'll leave there. Next question.
Yeah, no, it's from my perspective, because most machine learning hardware companies would think of is just providing the device, and it seems like you're going after what could be the host, the device, and then all the different combinations of, well, how big do you want your chiplet, how many cores, what sort of cores you want. This is where I think Tenstorrent is differentiating compared to some of the others in this space, and that's just a function of the expertise you have on the team.
Yeah, so you have to think, so this, at some point customers want solutions, right?
Yeah.
I want this computer. So if you go into data center, there's a server, it's really well defined, and there's the top of rack switch that's defined, and there's the SAN or the LAN, and there's storage computers, network computers. And sometimes they're all integrated in the same server, and sometimes there's these servers are for storage, these servers are for interfacing to a gateway. So there's a lot of differentiation in that. Today, AI is mostly accelerator cards in a server. People want disaggregated AI.
Yep.
So we'll see how that develops. Building chips with AI compute and general purpose compute right next to each other means that when the AI and those guys need to talk to each other, they don't have to go out somewhere with that latency, power overhead, and everything else. How that develops is going to be, complicated and organic. Like we could make this AI chip with, CPU and AI, and they're really busy, and they're still sitting behind a server that's fronting some other pile of applications. But there could be another application where now we have a single chip solution. You put it on a board, you hook up some sensors, you have an edge server. And it doesn't require a quote host computer. And how that develops, it's anybody's guess.
So, at what point will you be drinking your own Kool-Aid using Tenstorrent hardware to develop future Tenstorrent hardware?
Soon.
Soon.
So everybody on the planet's aware of GPT, ChatGPT now, and GitHub Pilot. So GitHub Pilot's been out for a while. It helps people write code. I've asked our engineers to start using that. Some of them think it's ridiculously good for helping you on the easy code. Andre Karpathy said it writes 80% of his code 80% correct, which if you're familiar with programmers is not a bad line. Yeah. You'd like to be 90-90, but it'll get there. It's pretty young. A woman in our HR group used it to write some HR policies at ChatGPT. She said it was really funny, and it's pretty good.
So guy over there has written some social posts assisted.
Yeah, so what I think, you start to use it in general. It's going to be part of the toolkit. It's very obvious it's going to be good at writing test bench and structures. And we're thinking about, all right, so we have a methodology about how to build and test hardware and build and test software. And you typically build frameworks so that supports all the tests, and then the tests are easy to generate, and they have widgets in them that check. So now can we train the model so that it knows about our framework and those widgets so it can auto-generate tests? That's a fairly obvious path, but it's engineering work to do. We think it's going to be able to generate RTL, and then it's going to start to generate code that's different from how humans write code. And then this is the thing, and this is my bet. It's one that every once in a while you see these things and you go, I can't unsee it. The AI code generation is going to make programs that are different from people, and the computers that accelerate that the best are going to be different than the ones we build today. So us having really solid AI foundation hardware computers and CPUs means that as we figure that out, we're going to go build new computers that are better at running that software. And that's a positive feedback loop. And because we have the capability to do AI hardware, software, and CPUs with all the collateral that goes around that with the team using AI to do it, we think we're going to be, let's say, well-positioned to go make those next architectural steps. And that's a fairly big intellectual statement, and we're getting into it, and as best I can tell, like Lubijan and I have talked a lot about this in the last 2 years, and as we've sort of gotten into it, it seems like we're directionally correct, and we're going to keep going.
Does it worry you that the initial outputs of those models create designs that are uninterpretable? So when it comes to debugging or edge cases, you can't actually go in. It's just
So this is one of the arguments, like in autonomous driving. Don't you want some part of the code to be written by humans, right? Because you can audit it. Mm-hmm. And I'm thinking, really? You have 5 million lines of code written by 100 people over 5 years, most of whom no longer work at your company, and you think that's auditable? It's not. With AI, this is the really funny thing. If you have a good data set and you have good training, you can actually train it to a loss function. You have a known loss function, right? The weird thing about the big C program is it doesn't have a loss function. You have no idea where its sharp edges are, where its complete failures are.
Yeah,
right?
That's fair.
You know, how long did they ship Windows? And everybody's using it at blue screens on a regular basis, right?
You've been using
so that's the auditable software that, you know, you think AI is like inferior to?
Well, this
is, you know, and then the other mysterious thing is the people who wrote the code, human beings, they also appear to mostly have intelligence, and they're not auditable either. We don't live in an auditable world.
I was going to say, but now
that ship sailed with Adam and Eve.
I guess you could say that even modern hardware, the hardware itself isn't auditable. I mean, how many features exist that?
Yeah, so I've learned this lesson painfully over the years. So the most important thing is abstraction layers, good clean boundaries, because we're not getting any smarter. I've said this many times. Like humans think they're getting smarter or something. It's not true. We're not getting any smarter. We build more complicated things, but those complicated things need to be built out of components that somebody understands. And what happens a lot is you have a really great design, and then you add stuff to it for 10 years, and people come and go. And at some point, it starts to get fragile, and people say, wow, it's getting complicated. No, it just turned into a mess. Like, you didn't do the right thing. At some point, you should have stopped. You should put your pencils down, broke it into pieces, made sure each piece had an owner that understood it, and the interfaces between them had a human-readable set of transactions that you can verify. And so hardware that's well-designed is fairly predictable and understandable. Hardware that's been growing like a furball. There's a paper called Big Ball of Mud. I love it. Everybody should go Google Big Ball of Mud and look at the paper, because it's literally the definition of disaster for software, and hardware does the same thing.
I think that goes back to points you made previously about ripping everything up and starting again with a new baseline more frequently than people tend to want to do.
Yeah, I say 4 to 5 years. The right number is really 3 years, because it'll take you a year to get over the fact that you have to do it.
Or the year that you're still behind your previous design, yeah.
Yeah, you have to, if not redesign, refactor, and be willing to do that, because you will slowly get to a point where it's so complicated and fragile you can't touch it. And then what do you do? And then something goes wrong, and you literally create something you can't control. So back to the AI point. The weird thing about AI is you have a new model, you have a new data set, you have new, let's say, error functions, and you train it. You can regenerate what it does. The big language models, it's not reasonable, but most models in a reasonable amount of time, in a way that you could never regenerate your 5 million lines of C code, or all your RTL, or all your historical infrastructure. So AI is pointing to a future that actually moves faster, not slower. And Steve Jobs had a great quote about that. The future accelerates. So your future has to move faster. So you can't be in a situation where the more successful you are, the more legacy you have, the slower you move. Let's say contraindicated with an accelerating future.
So does that mean the most comfortable we will ever be is today?
It's yesterday.
Well, yesterday, yeah.
Yeah, today is uncertain. Yesterday is already done.
Yesterday was the most comfortable.
That's why people love the past, because A, they selectively edit their memories, and B, it's not uncertain. Like, there's no uncertainty what happened to you 10 years ago. You may be sad about it or something, but you're not going to be surprised. So the future is a daunting place. It's a funny thought, isn't it? I hadn't thought about that.
Bringing it back to the topic at hand, the reason why I'm here, with the Tenstorrent strategy. Last time we spoke, you said something that resonated very well with me that I've actually used in presentations before. Mm-hmm. The fact that you've got to have one core that looks like one chip, that looks like one system. Has anything changed?
No. But, well, I've thought about this a lot. So if when the world of computing started, you just naturally had 1,000 processors, all the software development would have been, how do I coordinate across 1,000 processors? But from 1950 something to, 2005, most people programmed on one computer, right? So the computer was a single thing that literally executed instructions at the PC. And for most of that time, they were doing one instruction at a time. So now the GPU guys, by the time it was programmable, they had 1,000 threads. So they were starting to think about it, but their mindset in the programming model was still a single thread execution replicated lots of times. Like
a GPU.
Yeah, so we call that a vector of scalar programs, and which is a curious thing. But now you want to write one program that goes and engages thousands of processors. And to be honest, you're willing to tolerate some serious inefficiency to make that happen, right?
Yeah.
And somebody's saying, like using ChatGPT to write stuff, it does wild things like produce paragraphs that are novel, but it also figures out where to put the punctuation. Now, the punctuation could be done with a simple C program. There's two spaces, at the end of some number of words, put a period or a comma. Yeah. It's not rocket science. And you think, using ChatGPT to do something a C program can do, that's literally petaflops of compute for a second to put a comma, right? As opposed to 100 lines of C program. But the truth is, your brain has 10 to the 18th or 20th operations, and you're willing to ponder for a half a second where to put the comma. You don't think that's inefficient. You think,
well, you could argue that those calculations are ill-defined.
We use massive computers to do really simple things. My daughter was standing at the refrigerator trying to decide whether to have orange juice or milk. It's 10 to the 18th operation a second for 3 seconds. That's 3 times 10 to the 18th. That's a really large number of operations.
It reminds me of that weird statistic about how a Google search is equivalent to, boiling a kettle for a cup of tea or something.
Yeah, so when it's possible. So the thing is, AI and intelligence in general puts everything in a domain where you can think about things and make some kind of choices. And that's a really interesting phenomenon. The fact that, yes, now we could build a computer with 1,000, we're building a computer with 1,000 chips, with 200 cores in each one. That's 200,000 processors. And we want to program that from a simple program through a software stack that lets you write a program as if you're executing this program and deploy it onto something that looks like hundreds of thousands of minions, doing pieces of it.
Yep.
And, it's kind of stunning to think about, but your brain has tens of billions of neurons that are essentially doing the same thing. They're all little computers coordinating with each other. And so it's the natural act. And, Amazon's Lambda was a thing like that. Program in a high-level language to deploy thousands of cores without having to think about cores. And I'm sure it's absurdly inefficient per thread.
Yeah.
But it's absurdly efficient from a point of view of intention to action, which is what we're optimizing for.
So you just said building a computer with 1,000 chips, 200 cores per chip. Again, another thing you said when we last spoke was you need to find customers who want to build chips with 100 chips to go after the customers that want 1,000, then build 1,000 to go after the customers 10,000.
Well, yeah, so what we don't want to do is sell to somebody who sells to somebody who sells to somebody who has a problem they can't solve. Right. So what I want to do is we want to build AI computers that are usable, programmable, and then in the short run sell them to people who want to program AI computers. And they're going to start small, 10, 1, 10, 100. and then they're going to go, this is good, and they're going to scale up, and we're going to scale up, and then we'll sell to more people. And at some point, we'll sell to somebody who sells to somebody. It's like we want to, progressively do this because the AI software stack and the scaling of that in every dimension is difficult. And we think we have a good plan to do that, and we've engaged with a bunch of people about it. And scaling in multiple dimensions is useful, but the single core to 1 million cores in a software stack that can do that flexibly is the mission. And at some point in time, that'll be a fairly regular thing to think about, but right now it's a technical problem.
Have you ever thought about selling PCIe cards with your chip at retail, like a GPU, just an accelerator that people can buy off the shelf? Because I've had a lot of requests for that. Yeah,
we're going to do that. Like about a year and a half ago, we started to rev up. We ordered thousands of cards. We had a reasonable number of models running. We thought we were going to start to sell, small volumes to people who wanted to take them, experiment with them. And then basically two things happened. The supply chain, the cards didn't show up, so we had nothing to sell. And we did not move steadily from like 10 models to 20 to 30 to 40. We kind of plateaued because some of our software assumptions broke as we went into more models and more complexity. So we did a fairly big pivot, and we rewrote our software stack, deeply. Now we're running the number of models we want, and then we work through the supply chain issues, and we now have a reasonable number of cards, and I hope pretty soon we'll be able to sell, let's say, retail AI cards.
Yeah.
But I really want to do that after we go through a reasonable number of engagements with people who are pretty close. They go, well, we got these models, we ran for them, they bought the computers, they installed them, they worked. They iterated, they changed their software, they're relatively happy, or they threw us some bugs. We're going to open up our software stack so people can look at it. So the weirdest thing in the world is you buy a product with software stack, you write a program, and you get an error message from a piece of software you never heard about. Right? So we need to go work through that with people to say, here's how the software stack works, here's how the error messages are funneled out, here's how you successfully write complicated programs and debug them and work on it. But we're on the way on that. And then we will sell, cards to people. And the cool thing about that is then people think of all kinds of crazy things to do with them. And, I'm not a big believer that AI is going to show up in places that nobody expected. Like I've been in places that said, oh, we know the 5 strategics, we're just going to target them. I was at SideBite, we talked to hundreds of people, we had 100 design wins. Some of them were unexpected, and the ones that did the most revenue at the end of the day weren't the obvious ones. So I believe in a little bit of luck and that kind of stuff.
I always find that people who create the pickaxes are always the most surprised at where the pickaxes are used. that's
fairly colorful image.
And regarding current customer base and engagements, you haven't made any formal announcements yet. Do you think you'll be able to this year?
Yeah, we're going to. But again, I want to announce someone, like we have a picture of 2 happy customers holding our card, like a bunch of those. But I want them to use them for a while and, get legit feedback. Mm-hmm. Like we don't need to hype what we're doing. We're doing something that's really hard, You go to the moon, you don't have to make up a story about it. You just gone to the moon and came back, and,
You still need to hire the right people to do it, though.
Yeah. So yeah, we're on a good path. Like I'm happy with what we're doing. And when we have really solid, like this worked and these guys liked it, and these guys hated it. Yeah, we'll talk about that.